In the last few slides, we talked about what the perfect form boundary looked like in a prism or a block. Now we're talking about what a perfect form boundary looks like for a cylindrical part. Okay, so in this case we have the same tolerance, 1 inch plus or minus 10 thousandths, which means our maximum material condition is 1 inch 10 thousandths. So what we're showing here is a perfect form boundary here, that's these lines here, at the maximum material condition. So what we're depicting here is that inside this perfect form boundary, if my part was actually made within tolerance down to 990 thousandths, I have more room for surface variation, okay? Because perfect form is required at MMC. But as the part deviates from MMC, I have more allowance for form variation. Okay, so let's talk about straightness. We'll talk a lot about straightness because it sets up all of the other form tolerances. Straightness controls surface elements. It controls a derived median line. Surface line elements may be called a line element or a surface element. Derived median lines come from midpoints. We're going to talk about that in a second. And the center line is from the center of the feature. There is no variation to a center line. Okay, straightness applied to surface elements. Form tolerances are applied only if required. The required control is smaller than the size tolerance. Like I said before, you could put a real tight size tolerance on there and that will automatically control the form. That's per Rule 1 of GD&T. But if you want to use a larger size tolerance, then you might have to control the form to a tighter tolerance. Material condition modifiers are not used in form tolerance specifications applied to surfaces. Okay, so let's look at this one. Straightness of a flat surface. Okay, what we have here is a tolerance zone that's bounded by two parallel lines. The direction dictates by the view the orientation when applied in an orthographic view. So in this particular case, the direction the surface control applies to is just in this direction as it's shown. Now, the ways we can apply this tolerance is we draw the line showing the direction and we put a leader to it, or we put an extension line. It has to be in this view, mind you, because it means something else that was attached to this view. So we do it with an extension line or with a leader line, just like that. Those are the three ways to apply that tolerance. Okay, so here's what it means. Okay, so we have a perfect form boundary. Again, this is 875 plus or minus 5, so 880 max. That was our perfect form boundary at 880. Straightness tolerance is only in this one direction. And then we have a 5,000 straightness tolerance zone. Okay, so what we have here is you have the this 5,000 straightness tolerance zone. That depends on where the minimum and the maximum for that surface is on that line. And again, it only applies in this direction. So how will we test that? Here's how we would test that. So we're going ahead a little bit, but what we're using here is a surface plate with some gauge blocks to set this angle up at the right, and then we're going to check straightness of that surface. So what we're going to do is we're going to use a dial indicator, full indicator movement. Okay, so that dial indicator, as we scan it over the surface, is allowed to move a total of 9 thousandths, and still the part would be good. So that's how we check a straightness on a surface. Now, straightness on a surface element, again, it's always in this one direction, the straightness. Okay, so essentially what we're doing, we're checking the straightness of the surface element here. Feature control frame with extension lines or leaders, that's how we can do it. This one here, or we can do it with extension line here. That's how to apply that feature. Okay, so verification of surface straightness. You use a dial indicator. The full indicator movement is how far the indicator travels. And then total indicator reading is TIR. So you use a straight edge and a feeler gauge. Again, I showed you this slide before. This is how you would check straightness. Now, noted exceptions to Rule 1. Function determines exceptions to Rule 1. Specify on a feature of size a form tolerance larger than the size tolerance. Okay, because remember that's just not proper. Okay, so in this particular case, specify a feature of size, a form tolerance larger than the size. Show the form tolerance and independently symbol. Okay, so here's what we have is we have a size tolerance of plus or minus 3 and then a form tolerance of plus or minus 10. So what we have here is our form tolerance is larger than the size tolerance. Okay, and the only way for that to happen is if it's interdependent. This is kind of like a flimsy gasket part or something like that, where we have a tolerance, but we have a form tolerance that exceeds that tolerance. Here's straightness applied to a feature of size. Okay, and how we do that, how we know it's different than a surface, is that here's our feature of size. The size tolerance is here, and we apply the feature control frame right below the size tolerance. So that tells us that this straightness tolerance is applicable to a feature of size. How to interpret that tolerance? Okay, so we have 750 plus 10, that's 760. That's our maximum material condition. But we also have the straightness of 6 thousandths. So what we do is we add those three together, the 750 plus the 10 and plus the 6, and that gives us a diameter of 766. That is now our maximum outer boundary. Okay, and essentially what that says is our straightness tolerance zone diameter of the center line of the part is a diameter of 6 thousandths here. That is the form tolerance on the axis of the part. Okay. Okay, number 27. How to interpret this tolerance. Okay, so here's where we get into the idea of virtual condition. If we have an MMC of a shaft plus a tolerance, that gives us a virtual condition. Okay, so in this particular case, we have 1.250 plus or minus 10. The maximum material condition is 1.260. That's showing here. But we also have a form tolerance of 7 thousandths. So if we add our form tolerance to our MMC, we get the virtual condition. Okay, so the virtual condition is essentially the MMC plus the form tolerance. We're going to be talking about virtual condition a lot in this class. Okay, so in this particular case, we got 1.267. That's our boundaries. That's our virtual condition boundaries. It takes care of the MMC of the part plus the straightness tolerance. Okay, so what this says here too is, now that we're applying this MMC here, is that as we deviate from the maximum material condition, we're allowed more form tolerance. Okay, so what this table here says, when I make my part right at the MMC, which is 1.26, I only have 7 thousandths form tolerance available, because if I went outside the 7 thousandths form tolerance, I would violate my virtual condition here. However, if we make this part 1 thousandth below the maximum material condition of 1.259, we actually have 8 thousandths allowable tolerance. Okay, so what happens is, as the part dimension, the actual part measurement, deviates from the maximum material condition, we get extra tolerance. Now, it's kind of intuitive in that as you deviate in size here, you can allow more form variation and your part still fit within the function. So I'm going to stop this one right here.